In this lecture, we'll solve mass balances for reactors in which multiple reactions occur. Here's an example of two reactions that might occur in a reactor. The first is the desired reaction. This is a reaction in which ethylene, C2H4, we'll use the letter E to represent ethylene, reacts with oxygen to form the desired product ethylene oxide, C2H4O, and we'll use the letters EO to represent that molecule. This is a partial oxidation reaction. An oxygen atom adds to the molecule. A competing reaction is complete combustion of ethylene to CO2 and water. This is essentially burning the ethylene. For each reaction, we can assign an extent for that reaction. Xi1 represents the extent of the first reaction, and Xi2 represents the extent of the second reaction. To compute the generation minus consumption contribution to the mass balance for any of the species in these reactions, we have to sum up the contribution from each of the reactions. And each of the reactions will use the extent of reaction to do that. For the first reaction, we'll take a plus or minus, a plus if the species is a product, a minus if it's a reactant, times the stoichiometric for that species for the first reaction, the stoichiometric coefficient for that species for the first reaction. That's what this nu I, 1 represents. This is the stoichiometric coefficient nu for species I in the first reaction. So if I is E, for instance, in the first reaction here, the stoichiometric coefficient is 1. So we'll take plus or minus the stoichiometric coefficient for each species in the first reaction times the extent of the first reaction, plus or minus the stoichiometric coefficient for the second, for each species in the second reaction times the extent for the second reaction. All we've done is just add in an additional term, acknowledging that there can be consumption or generation in the second reaction or third reaction or fourth reaction that may occur in the reactor. Let's apply this to calculate the generation minus consumption term for each of the species in these two reactions here. So in these reactions, we have 5 species: ethylene, oxygen, ethylene oxide, CO2, and water. So we're going to go through each of these. To calculate the ethylene that comes out of the reactor, Ne, O, we'll take Ne, I, the ethylene that comes in, and subtract off then the contributions from the first reaction to the generation minus consumption and the contribution from the second. So for each, we'll start off by identifying whether it's a product or reactant. So ethylene in the first reaction is a reactant, so we'll put a minus here. The stoichiometric coefficient for ethylene is 1, and we'll multiply by the extent of the first reaction, Xi1. Now we'll move on to the second reaction. In the second reaction, ethylene also is a reactant, so we'll put a minus. The coefficient is also a 1, and we'll multiply that by the extent of the second reaction, Xi2. So the ethylene out is equal to the ethylene in minus Xi1 minus Xi2. Let's move on to oxygen. To calculate the flow rate of oxygen out, we'll take the flow rate of oxygen in, and then we'll look at each of the contributions from the reactions. First, oxygen is a reactant, so we'll put a minus here in the first reaction. The stoichiometric coefficient in the first reaction is 1/2, so we'll put 1/2 here, then multiply by the extent of the first reaction. If we look at the second reaction, oxygen again is a reactant, so we'll put a minus. The stoichiometric coefficient for oxygen in here is 3, so we'll put a 3, and then multiply by the extent of the second reaction. Now let's move on to ethylene oxide. The flow rate of ethylene oxide out is equal to the flow rate in. And let's look at the first reaction and see what contribution we have from that first reaction. Ethylene oxide is a product of the first reaction, so we'll put a plus here. The stoichiometric coefficient is a 1, and we'll multiply by the extent of the first reaction. Ethylene oxide does not participate in the second reaction, so there isn't a contribution from the second reaction. We move on to CO2. CO2 out is equal to CO2 in. And if we look at the first reaction, CO2 does not participate, so there's not a contribution from it. But it does appear in the second. It's a product, so we put a plus. The coefficient for CO2 in the second reaction is 2, and we'll multiply by the extent of the second reaction. We find the same thing for water, that the water out is equal to the water in. There's no contribution from the first, but from the second, it's a product, so we'll put a plus. The coefficient is a 2, and multiply by the extent of that reaction. So this really just builds upon what we've learned already. We just now have to look at each reaction when we calculate the generation minus consumption term to determine the flow out of a reactant and or product. We're going to introduce some additional terminology to handle reactors that have multiple reactions. The first is the term yield. Yield is defined here as the moles of the desired product form divided by the moles of the desired product form if complete conversion of the limiting reactant to the desired product occurred. Let's apply that to calculate the yield of a reactor in which these two reactions occur, and we acknowledge that ethylene oxide is our desired product. So the first term we have to calculate in parentheses in this formula here is the moles of the desired product form. Well, the moles formed is just going to be the moles of ethylene oxide out minus the moles in. The difference is how many moles were formed in the reactor. Then we'll divide that by the amount of the ethylene oxide that would be produced if we had complete combustion of the limiting reactant. Now here we're going to assume that the limiting reactant is the ethylene. So if we have NEI moles of ethylene coming in, the number of moles of ethylene oxide that would come out with complete conversion would be equal to the number of moles of ethylene that come in. Because according to the stoichiometry of the reaction, for every mole of ethylene coming in, this first reaction will produce 1 mole of ethylene oxide out. So if we have NEI moles of ethylene coming in, the maximum we could produce of the ethylene oxide coming out would be NEI, the maximum number of moles. So this NEI represents the moles of ethylene oxide that could be produced if we had complete combustion or complete conversion of the ethylene to ethylene oxide. From the expressions that we've written up here, we can calculate the moles of ethylene oxide out minus the moles of ethylene oxide in. This equation right here tells us that that difference is just Xi1, the extent of the first reaction. We'll simply divide that by the moles of ethylene that are fed in order to calculate the yield. Another term we're going to introduce is selectivity. This is defined as the moles of the desired product form divided by the moles of the undesired product form. Here, the moles of the desired product form is just going to be, as we discussed in the previous slide, the moles of ethylene oxide out minus the moles of ethylene oxide in. This is the moles that were formed in the reactor. We'll divide that by the moles of the undesired product, and we'll use CO2 to represent the undesired product. So the moles of the undesired product form are going to be the moles of CO2 out minus the moles of CO2 in. From the expressions we've written here for the moles out in terms of moles in, for ethylene oxide and CO2, we can show that the moles of ethylene oxide out minus moles in is just equal to the extent of the first reaction, Xi1. And the difference between the moles of CO2 out and the moles of CO2 in is just 2 times the extent of the second reaction. So the selectivity is Xi1 divided by the product of 2 times Xi2. We're going to work a problem in which we're going to perform mass balances around a reactor that forms formaldehyde. Just some fun facts about formaldehyde. It was the first polyatomic organic molecule detected in space. It is naturally occurring and has a variety of uses. Probably one of the ones that you're most familiar with is as an embalmer. So in this problem, we're going to make ethylene oxide from methane. So methane, CH4, which we're going to represent by the letter M, reacts with oxygen over a catalyst to form formaldehyde. This is very similar to the reaction we just talked about. It's a partial oxidation of methane to CH2O, which we'll use the letter F to represent formaldehyde. Unfortunately, methane also burns. This is natural gas, and we use it for heating as well as for transportation, but methane also is oxidized, completely combusted to form carbon dioxide and water. The two reactions are shown here. The first is the desired reaction in which methane reacts with oxygen to form formaldehyde. The second is the undesired reaction, which is the complete combustion. Now, as with the example we just talked about with ethylene, forming ethylene oxide, we probably will run this process with an excess of methane so that oxygen is the limiting reagent. Because if we add too much oxygen, then we'll promote the second reaction, the complete combustion reaction, to form CO2 and water. Now what I'd like for you to do is to pause this presentation, and for an equal molar feed of methane and oxygen and a basis of 100 moles total of the feed, I'd like for you to draw and label a process flow chart in terms of the component flow rates. So I highly recommend that you pause this presentation now, take a piece of paper and pencil or pen, and draw a process flow diagram and label it before proceeding. Well, I hope that you did take the time to attempt to draw out this process flow diagram. What you should have drawn is shown here. We have a stream for which we assumed as a basis 100 moles per second of a feed, and we're told that it's equal molar, so that the mole fraction of methane is equal to the mole fraction of oxygen is a half. Those are the only two components in the feed. All the other mole fractions for formaldehyde, for CO2 and water are 0. So we can calculate the flows of each of these components from the mole fraction times the total. So the flow rate of methane is just a half times 100, which is 50. The same is true for oxygen. And the flow rates of the other components are 0. Unfortunately, we know nothing about what comes out. We don't know the total flow rate, nor do we know the mole fractions of any of the components, nor do we know the molar flow rates of any of the components. So we have to represent each of these with an unknown. Here, we'll use N sub M0 to represent the flow rate of the methane out. The first letter indicates the species. The second letter O represents out. And the same notation is used for the other components here. We're going to try to solve this problem using atomic balances. Before doing so, though, I'd like to perform a degree of freedom analysis to see if the problem is indeed solvable. So now what I'd like for you to do is to pause the presentation and to perform this degree of freedom analysis by first of all counting the labeled unknowns for a control volume around this reactor, and then counting the number of atomic species, also counting the number of independent, inert, or non-reactive species, and then any other equations that we might have. What we're going to do is we're going to subtract from the unknowns the independent atomic species, the inert or non-reactive species, and any other equations. If the sum is equal to 0, then the problem is indeed solvable. So take a moment now and try to do this on your own. Well, I hope that you took a moment to do that. What you should have found is that there are 5 unknowns. Let's look at this problem and see if we can identify all 5 of those. And we want to count the unknowns by either looking at the mole fractions and the total flow for each of the streams, or just looking at the component flows. We won't look at the total flow if we count the unknowns using component flows, because the total flow is just given by the sum of the component flows. Either way, if we look at this inlet stream, we know the total flow and all the compositions, or equivalently, we know all the component flows, so there's no unknowns. Let's look at the product stream coming out. If we look at the mole fractions, we have 4 unknown mole fractions, Y1 through Y4, plus we don't know the total flow, so there's a total of 5 unknowns. If we look at the molar flow rates instead of each of the species, what we find is that there are 5 unknown molar flow rates. So either way, we count 5 unknowns, so there's a plus 5 here. If we count the species that are present in the molecules that participate in these reactions, we find that there are 3: carbon, hydrogen, and oxygen. Those are the only 3 atoms that participate. There's no inerts in the feed, so we'll put a 0 here for inerts. There's no other equations known right now, so we'll take the 5 unknowns, subtract off the 3 atoms that we have, subtract off 0 for the number of inerts, and we end up with a plus 2. This means that we have 2 degrees of freedom, and that we need 2 additional specifications, or specs, in order to solve this problem. And what we're going to do, once we have these, is write for our atomic balances that what comes in for each of the species is equal to what comes out for each of the atomic species. So instead of providing the additional specs, I'm just going to go ahead and write out the atomic balances. And they're written here in the form that out is equal to N. And so let's review that. Let's first of all calculate the amount of carbon that comes out. And the way we're going to do this is look at each of the species in the outlet, in the stream that leaves, the effluent from the reactor, multiply the molar flow rate of each species by the number of carbon atoms there are per molecule. So we'll go through that and get some practice doing this. So the first species, molecular species that leaves, is the methane. So in methane, there is carbon. So we'll take the molar flow rate of the methane, NMO, and we'll multiply this by the number of carbon atoms there are per molecule, and there's 1. Next, let's look at the oxygen. Oxygen doesn't have any carbon in it, so there won't be a contribution to the carbon balance from the species. If you look at formaldehyde, there will be a contribution. So we're going to take the flow rate of formaldehyde, NFO, and multiply it by the number of carbon atoms there are per molecule of the formaldehyde. Here's the formula for formaldehyde. It's CH2O or HCHO. There's only one carbon here, so we'll put a 1 in front of the NFO. Let's move on to the carbon dioxide that might be produced. There is carbon in this, so we'll take the flow rate of the carbon dioxide, NCO, then multiply by the number of carbon atoms that there are per molecule of CO2. And there's only one. CO2 has 1 carbon per molecule, so we'll put a 1 here. And there's no carbon in the water that comes out. So the sum of these three terms here is equal to what comes in. We'll set that equal to the carbon that comes out, or this is what comes out. We'll set that equal to the carbon that comes in. The carbon that comes in, we'll first off look at the methane that comes in. It has a flow rate of 50, and we'll multiply that then by the number of carbon atoms that there are per molecule of methane. There's only 1, so we'll put a 1 here. And so what we'll do is we'll set the flow rate that comes out of carbon to equal to that which comes in. Can't solve for any of the unknowns here now. Let's move on to the hydrogen balance. Once again, we'll look at the output, the effluent from the reactor, and calculate the flow rate of hydrogen atoms that come out. And we'll go through each species and determine the flow rate of hydrogen associated with each. Let's start with methane. Methane does have hydrogen, so we'll take the flow rate of methane that comes out and multiply by the number of hydrogen atoms per methane molecule. There's 4. So 4 times the flow rate of the methane coming out will be equal to the flow rate of hydrogen coming out. Let's move on to oxygen. Oxygen doesn't have any hydrogen, so we'll have no contribution from it. Formaldehyde will give a contribution to the hydrogen flow out. We'll take the flow rate of formaldehyde, multiply it by the number of atoms of hydrogen per molecule of formaldehyde, and look up here at the formula, we see there's 2. So 2 times the flow rate of formaldehyde out is a contribution to the hydrogen flow. If we look at CO2, there's no hydrogen in the CO2, so there won't be a contribution from this. Finally, we'll look at the water. Water does have hydrogen, so we'll have to include a contribution from the water flow out. I'll take the water flow out times 2 hydrogen atoms per molecule of water. So the sum of these three terms is the flow rate of hydrogen out. We'll set it equal to the flow rate of hydrogen in. Hydrogen flows in only with the methane, and we'll multiply the methane flow rate by 4. The 4 atoms of hydrogen we have per molecule of methane. We know the flow rate of methane coming in is 50, so 4 times 50 is 200. And we'll repeat the very same thing for oxygen. We'll go through this in some detail here. If you find that you don't need to do this, you can just simply move forward by pressing the right arrow key in order to go to the next slide. Let's calculate the flow rate of oxygen coming out by once again going through each and every species and determining if it has oxygen, and then including the contribution to the oxygen atomic flow out from that species. So let's start off with methane. There's no oxygen in methane, so this will not contribute anything to the flow rate of oxygen out. Next, let's look at the oxygen that comes out. Well, if we know the flow rate of the oxygen molecules that come out, that's NOO, let's multiply that by 2. There are 2 atoms of oxygen per molecule. Let's move next to the formaldehyde. Formaldehyde does contain oxygen, so we'll take the flow rate of formaldehyde and multiply by the number of atoms of oxygen per molecule. There's only 1. Next, let's look at the CO2. We'll take the flow rate of CO2 times 2 atoms of oxygen per molecule of CO2. And finally, we'll move on to water. Water has 1, so we'll put a 1 times the flow rate of, there's 1 atom of oxygen per molecule of water, so we'll put a 1 times the flow rate of water. Sum of these four terms is the flow rate of oxygen in. We'll set that equal to the flow rate of oxygen out. This is flow rate of oxygen out. We'll set equal to the flow rate of oxygen in. The flow rate of oxygen in is equal to the flow rate of the oxygen molecules that come in times 2 atoms per molecule. The methane does not contribute here to the oxygen flow rate in. Since we know the oxygen flow rate in is 50, 2 times 50 is 100. That's how we get that third equation. Unfortunately, if we look at this, we have 3 equations and 4 unknowns, or 5 unknowns. We're sort of stuck unless we get 2 additional specifications. Here's one of the specifications that we're going to use. This is a common one when designing a reactor, and that's conversion. In particular, we're going to talk about the conversion of methane. We're going to assume we know the conversion of methane. It's specified as 90%. or the fractional conversion is 0.9. Conversion is defined to be the amount of methane consumed divided by the amount of methane fed. We can calculate the methane consumed by taking the difference between the methane in and the methane out. Methane in minus methane out is the amount that was consumed. We'll divide that by the methane that was fed. So if we plug in, we know that the methane in is equal to 50. Subtract off the methane out. Take that difference and that quantity and divide by 50. Set that equal to 0.9. A little bit of algebra allows you to solve for the methane out. The fluoride methane out is 5. So we can add that here then to our stream. It's information for that stream coming out. We still need one more specification. The next specification is going to be the yield. The yield of formaldehyde. Yield is defined as the formaldehyde produced divided by the amount that theoretically you could produce with complete conversion of the limiting reactant to formaldehyde. So the theoretical amount, the amount that we'd have with complete conversion of the limiting reactant to formaldehyde, we're going to calculate because we know the limiting reactant is methane here. We're going to take that as the limiting reactant. Actually, if you look at just this reaction here for the production of formaldehyde, the two are in a stoichiometric ratio. So what we're going to use for the calculation of the theoretical amount of formaldehyde produced, the flow rate of the methane coming in to calculate it, because that's what we really want to do is convert all that methane to formaldehyde. So we have 50 moles of methane coming in. If we were to convert all that to formaldehyde, according to the stoichiometry of this reaction, we get 1 molecule of formaldehyde per molecule of methane. So we'll multiply by 1 mole of formaldehyde per mole of methane, same thing. So we multiply 50 times this ratio of 1 to 1, we just get 50 moles of formaldehyde that we could theoretically produce from 50 moles of methane. It's pretty obvious that there's 1 to 1 conversion. The yield is going to be equal to the amount of formaldehyde produced divided by the theoretical amount. Well, the amount that's produced is the formaldehyde out minus the formaldehyde in. Since the formaldehyde in is 0, the amount that's produced is exactly equal to the flow rate of formaldehyde out. We'll divide that by the theoretical amount that we could produce, which is 50. We'll set that equal to 0.855. We're going to assume 85.5% conversion, or yield, 85.5% yield. So simply rearranging this, we can calculate the formaldehyde out as 42.8. We'll add this number then up to our stream information. Now we should be at a point where we can solve those atomic balances for the unknown flows. And we're going to do that. What's shown here are the atomic balances that were written for carbon, hydrogen, and oxygen, simply rewritten. So the first is that this is on the left-hand side of the equals is the flow rate of carbon coming out. We'll set that equal to the flow rate of carbon coming in. Now we know the flow rate of methane out is 5, but formaldehyde out is 42.8. The only thing we don't know is the flow rate of carbon dioxide out. We know that this is all equal to 50. That's the total flow rate of carbon in. It allows us to solve then for the flow rate of carbon dioxide out. It's 2.2. Let's move on to the hydrogen balance. This is the total amount of hydrogen that comes out. We can calculate this as 4 times the flow rate of methane, which we now know is 5, plus 2 times the flow rate of formaldehyde, which we now know is 42.8, plus 2 times the flow rate of water, which we don't know. We set that equal to the flow rate of hydrogen coming in, which we're able to calculate as 200. This gives us an equation we can solve for the flow rate of water out. We'll go through the details of that algebra, but you should find that the flow rate of water coming out is 47.2. The last unknown is the flow rate of oxygen coming out, and we're going to use the oxygen balance to determine that. So on the left-hand side here is the flow rate of oxygen out. This is equal to the flow rate of formaldehyde, which is 42.8, plus 2 times the flow rate of CO2, which is a 2.2, plus 1 times the flow rate of water, which is 47.2, plus 2 times the flow rate of oxygen out. That's equal to oxygen in, which we already determined is 100. This is an equation we can solve pretty easily for the flow rate of oxygen out, and we find it's 2.8. So we completely solved the problem. We completely determined the flow rate of the stream that leaves the reactor. We have a choice of what type of balances we use when we perform mass balances around a reactor. One choice, potential choice, is using atomic balances. I'm going to compare that, let you compare that to trying to solve the mass balances around this reactor using extent of reactions instead of atomic, which is molecular species balances instead of atomic balances. Before doing that, let's go ahead and do a degree of freedom analysis. We should find the same thing, that we need 2 additional specs in order to solve this, the 2 being the ones we just talked about. But if we were to do a degree of freedom analysis based on extensive reaction, we would have to count the labeled unknowns and add to it the number of independent reactions, and then subtract off the number of independent reactive species, number of independent inert or non-reactive species, and then any other equations that we might have would be subtracted. Take a moment now and do this degree of freedom analysis on your own. Well, I hope you paused the presentation and did do that degree of freedom analysis. What you should have found is that the number of unknowns is 5, just as we determined last time. Now we have to count the number of reactions, which is 2. The number of species that participate in these 2 reactions is 5. Methane, oxygen, formaldehyde, water, and CO2. There are no inerts, so and there's no other specifications given right now, so if we simply add these numbers up, we find is that the sum is a +2, and we need we have 2 degrees of freedom, or we need 2 additional specifications. Before moving on to write the molecular species balance, let's write the molar flows out in terms of the extent of reaction. And so for each of the species, we're going to calculate the flow rate out from the flow rate in, and we're going to subtract off the generation minus consumption for each of the 2 reactions that you see here in the reactor. So let's start off with methane. So methane flow out is equal to methane flow in. We'll first off determine the contribution from the first reaction. We have to choose a plus or minus to begin with. Since methane is a reactant, we'll use a minus. We multiply by a stoichiometric coefficient for methane in the first reaction, which is 1. Then multiply by the extent of the first reaction. We have to do the same type of consideration to determine the generation minus consumption term for the second reaction. We have to ask, is methane a reactant or product in the second reaction? It's a reactant, so we'll use a minus. The coefficient in the second reaction for methane is 1, and then we multiply that by the extent of the second reaction, Xi2. Since we know the methane in is 50, then we can simply write this as 50 minus Xi1 minus Xi2. Let's do the same thing for oxygen out. Oxygen out is equal to oxygen in, and we have to determine the contribution, the generation minus consumption term for the first reaction. Oxygen is a reactant, so we'll use a minus. The coefficient for oxygen is 1, and then the extent of reaction is I1 for the first reaction. We go through the same considerations for the second. Oxygen is a reactant, so we'll use a minus in the second reaction. The coefficient in the second reaction is 2, so we'll put a 2 here, and multiply by the extent of the second reaction. And we'll simply plug in the known flow rate of oxygen coming in, of the oxygen molecules, is 50, the molar flow rate. Next, let's look at the flow rate of formaldehyde out is equal to formaldehyde in, which we know is 0. Then we'll have to look at the first reaction to determine any contribution from it due to generation or consumption. Formaldehyde is a product in the first reaction, so we'll put a plus. The stoichiometric coefficient is 1, and we'll multiply by the extent of the first reaction. So if we have 0, this then becomes 0 plus Xi1, which is Xi1. For CO2, we'll do the same thing. The CO2 out is equal to CO2 in. We'll examine the first reaction, see if there's any CO2 involved in it. There's not. It's only in the second reaction. In the second reaction, CO2 is a product, so we'll put a plus. The coefficient is a 1, and the extent of reaction is Xi2. So the flow rate of CO2 out will be equal to Xi2 since there's no CO2 coming in. NCI is 0. Next, let's look at the water out. The water out is equal to the water in. There's no water in, so we know that term is 0. Water does participate in the first reaction. It's a product, so we'll put a plus. The coefficient is a 1. Stoichiometric coefficient is a 1, and we'll multiply by Xi1. Looking at the second reaction, water is a product, so we put a plus. Coefficient is a 2, and we'll multiply by Xi2, the extent of the second reaction. So this term on the right-hand side here becomes just Xi1 plus Xi2. If we add these all up, we can get the total molar flow coming out. We find that total molar flow coming out is 100, which is equal to M1. Not surprising that the flow rate out is equal to molar flow rate out is equal to molar flow rate in, because we have 2 moles in the first reaction that react to give us 2, and we have 3 that react in the second to give us 3. Both reactions are equimolar. Next, let's make use of the 2 specifications in terms of conversion of methane and yield of formaldehyde to reduce the number of unknowns that we have. First, let's look at the methane conversion. Methane conversion, as we said, is methane consumed divided by methane fed. The methane consumed is just going to be the difference between methane in minus methane out. So methane in minus methane out is plus Xi1 plus Xi2. We'll divide that by the methane in, which is 50. That's going to be equal to 0.9. Unfortunately, we can't solve this for Xi1 or Xi2 yet. But let's look at the other specification, the yield. The formaldehyde yield, we're going to set equal to 0.855. That's a formaldehyde produced divided by the theoretical amount. We already determined that the theoretical amount of formaldehyde that could be produced from complete conversion of the methane would be 50 moles. So the yield is going to be the formaldehyde produced, which if we look at the expression for formaldehyde out, the formaldehyde out minus the formaldehyde in is the formaldehyde produced. That's equal to Xi1. So the formaldehyde produced is Xi1. We divide that by the theoretical amount, 50, and set that equal to 0.855, 85% yield. This is an equation we can solve for Xi1. So here are those 2 equations just reproduced on this slide. Solving the yield equation for Xi1, we get 42.75. Then we can solve the conversion equation for Xi2, which is 2.25. We're almost done. We can plug those values for Xi1 and Xi2 back into our expressions for the output flows of each of the components of the methane, the oxygen, the formaldehyde, the carbon dioxide, and the water. Doing so, you get the numbers that you see here, which are exactly equal to the numbers we got from our atomic balances. Why don't you take a moment and reflect on whether you thought it was easier to work this problem using atomic balances, or whether it was easier using the molecular balances and using the extent of reaction. The problem we're going to work in class is going to be a problem involving a reactor for the production of monochloroethane, or chloroethane. This has a wide variety of uses that you can see here. Probably one of the most significant ones is as a refrigerant or as a blowing agent. Now, unfortunately, because of the chlorine here, these fluorinated, chlorinated, or small molecule organics are ones that are considered an environmental hazard, are increasingly being considered environmental hazards and are being phased out. The problem we're going to talk about is a reactor in which we make the monochloro, but unfortunately, in the process of making the monochloro, according to this reaction here, which ethane reacts to form with chlorine to form the monochloroethane, is that we get conversion of the monochloro to the dichloro with additional reaction with chlorine. And as with the partial oxidation of methane or of ethylene in order to form an oxygenated product, here we probably want to keep the chlorine as a limiting reactant to prevent or suppress the second reaction here. If the ethane is in excess, and in fact could be in significant excess, then we'll consume most of the chlorine in producing the monochloro. We'll have, if chlorine is in a limiting reagent, then there won't be enough here to produce a significant amount of the dichloro. When we do have a process like this, in which we have one reactant and a great deal of excess, is that we don't want to waste that. So what we're going to do is make use of this process flow diagram we've talked about from the very first day of class, in which we have a reactor that does a transformation to produce a desired product. Then we send it to a separator in which we remove our desired product, the monochloroethane, from undesired products or byproducts, such as a dichloro and HCl, and allows us then to remove the unreacted reactants, in this case the ethane, and recycle it back to mix in with a fresh feed to the reactor. Now this particular problem, to solve it completely, we would want to look at the combination of this, the reactor and separator together, and do mass balances around it. For the problem in class, though, we'll only be focusing on the reactor part of it, just like we did here in this lecture. So in order for you to get ready, I would recommend you go ahead and start working on the problem. Here are the 2 chemical reactions with the letters we're going to use to represent each of the species. What I'd like for you to do is think about drawing and labeling a process flow diagram for the reactor in which you assume there's 100 moles of MCE in the product. This is a different basis than we've assumed in the past. This is not the total flow rate of the effluent from the reactor. This is the flow rate of this particular component, the MCE in the effluent. Also assume that the feed contains only ethane and chlorine, and that the reactor, all the chlorine is consumed. Next time we'll be working mass balance problems for reactors in which there is recovery and recycle of unreacted reactants. These problems are going to become much more complex as each problem involves in it 4 or 5 sub-problems, 4 or 5 mass balances we're going to have to perform for just one given problem. So we're going to roll up 4 problems into one. That's it for today. Bye for now.